Our next guest became fascinated by how ancient cultures adapted local materials for their structures. He became an architect with one foot in academia at the UBC School of Architecture and Landscape Architecture, and another foot in the business world, putting his ideas to work. He is challenging our assumptions about building materials in very surprising ways. Please welcome Joseph Dahmen.
Thank you, Sam and Lynn, for the invitation to talk tonight. I brought a couple materials with me here tonight. This one I grew from mushrooms and sawdust. It's quite light. And this one I made of soil, but it's heavy and dense and actually about twice as strong as concrete. They're different, quite different, but I think of them both as being soft, and I'd like to explain why that is and how I think softness is going to be key to helping us address the really pressing questions in the future of architecture. So, chances are you passed a building site on the way here tonight. It's a common occurrence here in Vancouver. We're building so much. And in the past few years, we've started to get serious about reducing the impacts of our buildings as we recognize the emissions all these buildings produce while we occupy them, mainly from heating and lighting them, just basic functions. We even have a framework for addressing that now called the Zero Emissions Building Plan. It just passed this past summer. And it means that in less than 15 years, the emissions from occupying all these buildings, the new buildings, will be zero. We'll eliminate emissions. It's really exciting. We'll do it by making higher quality buildings and by using more renewable energy, which is fantastic, but the trouble is the plan doesn't include the impacts of the resources we use to construct buildings. Materials like concrete and steel that you can see in the picture behind me. And these materials require a lot of resources and energy. In fact, 40% of all resources around the world go into our buildings. And none of this is included in the Zero Emissions Building Plan. So it's addressing a part of the problem, a really pressing part, but it's ignoring one that in the long term is going to be even more important when we eliminate the emissions from operations. We can see why when we look at a material like concrete. So concrete depends on cement for its binder, and that cement causes 7% of global carbon dioxide. And the reason is that to produce it, we mine the limestone that's shown in the bottom of the image, and we cook it. And when we do that, we release carbon dioxide that was trapped safely in these geological formations for millions of years and release it into the atmosphere. So we can look in contrast at how the body makes bones, and we can learn a lot. Because the body, unlike the process of making cement, actually draws from the material in its immediate surroundings. So it picks up minerals from the body. The bone itself has variable density, so it's densest where the stresses are highest and more porous where the stresses are lower. It's adaptable and grows with the body that it serves. And at the end of its life, it's biodegradable and can actually add nutrients to ecosystems at the end of life. So what if we could produce architectural materials in a similar way, using feedback loops between the building and its immediate environment, the building site? This might require a kind of sensory feedback loop similar to that of the bone. And if we can do that, the kind of material that we produce by engaging matter in feedback loops with the environment, I call soft. They require advanced sensing to accommodate the rich complexity of environment. But they're soft also because of the interrelationship of matter and information that enable them to operate in conjunction with biophysical systems instead of trying to obliterate or replace them, as is the case with a lot of legacy technologies. So let's look at what this might mean in terms of a concrete block, which is another way we use cement. This is the old way. We mine the limestone, as we just saw. We truck it to the cement plant. Once it gets to the cement plant, we put in a lot of energy, and then we truck that cement to the block plant. We put in more energy, and we truck the blocks to the building site, and then we build the building. It's a one-size-fits-all approach. All the blocks are the same strength. And it's, in a way, at every stage, it's using energy to eliminate variation. It's aiming for a kind of homogeneity that's akin to McDonald's. It's the same everywhere. So how do we rethink this process? Well, I actually it's not so difficult. I co-founded a company called Watershed Materials about 5 years ago to rethink the block from a soft paradigm, where we might start by using a range of materials, of soils, instead of just limestone and gravel and sand. We use dynamic data processing to characterize soil attributes and behaviors, so we no longer have to be afraid of variation in the age of big data. We can just process it. And then we can activate the natural clays that occur in the soil to provide the binding that we get from cement now. And so we can produce a range of different products from local resources taken from right where the building's going to be built. And they might be stronger where we want a foundation, or less strong where we use a partition wall. And we can achieve a whole different paradigm this way. We knew this could be done because traditional buildings have used rammed earth, was a technique that uses clay binders for 10,000 years. It's one of our oldest building technologies. So this is a wall I built at MIT back about 10 years ago that uses only clay to hold the wall together. And this is the third generation block prototype that we built with funding from the National Science Foundation in the US. And it uses these kind of computational protocols to enable it to sort a whole lot of soil. It's maybe it doesn't look so portable there, but on a truck we can get it to the building site where it produces a whole range of different blocks based on their function. So we built a few demonstration houses. This is in the Napa Valley, and this one is in Sonoma by Arc and Tilt Architects. But the point is these blocks meet all the performance criteria of ordinary concrete blocks with 50 to 90% lower carbon emissions. But the funny thing is that the architects are picking them up partly because they actually express the geological character of the site, so you can kind of see it coming through there. As soon as we get away from cement, we have a whole range of new expression possible. So you can check out what we're doing at watershedmaterials.com. We looked at one material that's a structural material. We can look at another that's insulation, which we're using actually to reduce the energy use in buildings as we recognize the importance of it. A lot of insulation actually ends like this because the average age of a commercial building in Canada is only about 40 years. So we asked the question with my partner and some students at UBC, could we actually grow insulation using natural processes from mushrooms, like the block you see in front of you? And it turns out you can. So you inoculate sawdust with mushroom spores and put it in molds, and about 5 days later it comes out like this. So this is some furniture we grew that we installed in front of the bookstore at UBC. Those are some of my research assistants there, our research assistants, a good-looking bunch. The materials can be a bit unpredictable, and so this was a mock-up wall we built that went through a temperature change and in fact grew these edible, they're organic oyster mushrooms. And clearly we don't want this happening in our walls, as we found out during the leaky condo crisis. But I think what's really amazing about these living materials is if you can imagine a day when we can actually control the growth process, so that at the end of a building's useful life, we could flip a switch, maybe with UV light or some genetic engineering, and turn on the mushroom decomposition, so that what might otherwise be an inert pile of toxic garbage would instead be offering us lunch. So soft materials engage architects in feedback loops at the limits of human control. And what we give up in absolute control, we might get back in a rich interrelationship with our local environment at regional and even planetary scales. So I think that this offers some real opportunities to architects working at the intersection of materials and culture. I've just got 2 slides left. We've seen how a soft approach can address the impacts of 2 of the most notorious materials in terms of carbon emissions, human health risks, and biodegradability. But I think what's really exciting is if we zoom out to the planetary scale, these materials suggest that the built fabric itself, rather than contributing to the destruction of the planet, could be our greatest hope for warding off climate change. Just as bones absorb minerals from their immediate environment, carbon-positive buildings whose materials store more carbon than they emit can act as the carbon sink that we so desperately need to avoid global warming. Thank you.